Yeah, thank you for this very warm welcome. I'm very happy to be here. I'm Max Eschenbach, as said, and today I'm representing one research group in particular, which is DDU, the Digital Design Unit of the Technical University of Darmstadt, led by Professor Oliver Tessmann. And together we focus on the fusion of creativity, computational design, technology and interdisciplinary research as the key to mastering the manifold challenges of our time. So within several related research trajectories, we develop computer-aided design methods and tools that are appropriate to the different materials and technologies. And currently, a big focus lies on the topic that I want to speak about here today, which is challenging or even flipping the order of conventional process chains. We research this by exploring the assembly of heterogeneous natural materials, like in Scanprint Assemble, reusing structural concrete components in the Precast Concrete 2.0 project, as well as investigating non-standard autonomous robotic assembly of discrete standard parts, like in the Tactile Robotic Assembly project. So, from digital real to real digital, what do we mean by that? From the 1990s onwards, computational design has been predominantly used by the first generation of digital architects in the context of mass customization of form. And this meant creating non-standard architecture from a large number of individualized components as digital fabrication technologies advanced and gained popularity. And of course, here you can only see a very few examples. So within this first digital turn, computational design and engineering was established in digital real process chains, or that's what we call them right now. Components were digitally designed and engineered and then subsequently materialized using digital fabrication to become real physical components. And today, the possibilities, but also the problems and challenges for architecture and the whole AEC industry have shifted in the light of resource scarcity and climate change. This is an image of the controlled demolition of one of the Pruitt-Igoe buildings in St. Louis. And while this project often serves as a poster child for the failures of public housing, I want to direct your attention to a different kind of failure. The construction of Pruitt-Igoe was modular and heavily based on prefabrication of components. Construction finished in 1955, and the first building was demolished only 17 years later in 1972. By 1976, all of the 33 buildings were demolished in a destructive manner, rendering all the contained modular components as waste, as well as destroying all the embedded design and engineering intelligence. Here is another, more recent example of demolition. The AFE Tower in Frankfurt, Germany, so that's where I'm from. In this case, the building was demolished in 2014, after 42 years of use, and still 8 years shy of the 50-year use phase that buildings are being planned for. It has to be mentioned that the structural framework of this building was completely intact. And this serves as an example of the fact that most buildings are not demolished because of structural damage, but more commonly because something else, something new with a different program should be built on the same site. And this leads to cases like this, where all structural components and all the design intelligence that is embedded and materialized within the building is destroyed. Only to build a building with very similar typology in its place that now serves as apartments and hotel instead of being a university building. And when I say destroyed, I'm fully aware of the fact that some of the building debris is nowadays being recycled, but in almost all cases, this will result in downcycling. Furthermore, recycling of construction waste into new materials is a challenge of material technology which affect design and planning only peripherally. The reuse and reusability of entire building components, on the other hand, are genuine architectural issues that touch on all aspects of sustainability. So, while architecture, engineering, and construction was and still is operating in a mostly linear material flow, we are now facing issues of resource scarcity and environmental concerns more than ever before. And as these will become even more pressing issues as time progresses, we as architects, designers, and engineers need to question, challenge, and rethink these conventional linear process chains. We need to find ways to design and construct in a more sustainable manner, and that means transforming our current linear process chains into circular process chains. So I want to introduce to you our current case study on a real digital process chain that enables us to reuse structural concrete components from obsolete buildings. This research focuses especially on the question, how can we reuse building components from obsolete buildings without destroying them? And what you can see here is our concept of our real digital process chain that we are currently researching and developing within a publicly funded research project called Precast Concrete Components 2.0. The whole process starts on the left by digitization of an obsolete building, which is then cataloged in a database. We then connect an architectural design to that database and identify components that we can reuse. And the chosen components to reuse are then refurbished using robotic tooling and then can be reused in the construction of a new building. And this new building from reused components can then again be disassembled and reassembled in the future. So let me explain this case study in a little more detail. To enable such a real digital process chain, a lot of technical prerequisites have to be taken care of, since it is fundamentally more complex than the already established digital real process chains. We call it real digital because it starts with real, already materialized components of our built environment and proceeds to combine them in a digital manner. And to enable such a process, we need to digitize and assess our inventory by 3D scanning and evaluating the components of a building that we are able to reuse. We do this by using 3D scanning technology of our partner Faro, and once we have a 3D scan of a building, we process the resulting point cloud using statistical outlier removal and random sample consensus algorithms. And this allows us first to identify geometric clusters and compute a geometric abstraction, as well as extracting the geometry of components to reuse, like columns and beams. We are then harvesting the components to be reused using controlled disassembly instead of demolition. Oh, sorry, this video seems to be a little flipped. And while doing that, we are linking these physical real-world components to our digital model based on the 3D scanning data. And each component gets a globally unique ID using an RFID tag so that the physical component can be identified later in correspondence to the digital model. So with the components harvested and digitized and inspected and assessed, we build a digital repository with our partners Faro and Think Technologies. And this database catalogs all the gathered information about the individual components, which includes not only geometric information, but also data on concrete quality, reinforcements, transport routes, embedded gray energy, etc. And this database can then be queried using a standard REST API, so that interaction with it can be integrated into further software services and potentially even into a trading platform for these reused or refurbished components. In parallel, together with the Institute of Structural Design at TU Brunswick, we are developing a construction system that is based on dry joint connection details, and this allows the already harvested concrete components to be refurbished for their future use. It is important to note that we do not take a kit of parts approach here, where the whole construction system is modular and only a predefined range of parts exist, as this would severely limit architectural designs. Instead, the connection details are predefined and refurbished, and we refurbish the components with minimal adjustments based on the design's demand. For fabrication of the connection details, the robotic equipment and experience at the Digital Fabrication Laboratory at TU Brunswick are being used. So, given all this information about the harvested components, we can now process architectural and structural design models using a demand-based matching algorithm. At the most abstract level, the computational problems to be solved are variations of the classical combinatorial problems in computer science, namely the assignment problem and the cutting stock problem. And by using the popular CAD software Rhino and Grasshopper and even extending it, we are able to identify matching components from our repository based on a given design input. I won't explain the whole pipeline here in detail, but of course I'll give an overview and you're welcome to ask about more details later. Currently, we are using mixed integer programming to compute these optimal matchings using the Gurobi solver, as this allows us to include differentiated constraints into the optimization process. So for example, structural constraints, transport routes, as well as data from lifecycle assessment can be included into the decision process and thus inform the optimization. And through that, we are able to overcome the limits of conventional matching algorithms, such as the famous Hungarian algorithm, which does not allow for additional constraints, but instead only operates on the single cost value. And by leveraging this computational model, we are able to create feedback loops between architectural design and engineering on the one hand, and our repository of available components on the other hand. And this allows architects, designers, and engineers to get feedback about where reused and refurbished concrete components can be integrated and what that means in terms of environmental impact. And throughout this whole process, we evaluate the environmental impact of our approach within an accompanying life cycle assessment. And here we compare the reuse of 1 cubic meter of concrete with the production using recycled concrete, as well as with the production of the same amount of conventional concrete. And so far, our results show that it is not only possible to build with reused components, but also effective in terms of CO2 equivalent savings, as well as lowering global warming potential. And in parallel to this rather technical research, we also ask ourselves what the idea of reusing building components means for architectural design and what kind of aesthetic language may result from it. And together with students, we are speculating about these questions, and here is one example of a student's work that had profound impact on our thinking of this process chain. The student envisioned a concrete hospital where concrete components are being refurbished. And already harvested components are aggregated to form intermediate and ever-changing structures, in this case, a bus stop that stores the discrete concrete columns. So a building can not only be made from reused components, but also serve as a physical repository for these components until it is disassembled and the same components are used elsewhere. Within our teaching, we employ prototypes of the computational design tools that we develop in research for the students. And students are then asked to experiment and get familiar with our research tools, as well as test them within given exercises and design briefs. In this way, we are able to connect research and teaching so that research informs teaching and vice versa. Here we see an animation of the combinatorial assignment process, assigning very heterogeneous 2D shapes to defined tessellation cells. And this is used by using what we call a shape descriptor, what you can see on the left lower hand side. And within this same design studio that was held last year, students also speculated on different strategies for connecting such heterogeneous pieces of rubble and debris. And the idea here was to let students think on how we can connect such heterogeneous parts using 3D printing, similar as to in the digital rubble project that you can see on the right. The computational design tool was then extrapolated for 3D scanned pieces of rubble and used by students to design and build a small-scale demonstrator. 3D printing was used to print the connecting components and join the pieces of rubble together. If we design and build with rather homogeneous reused components, like in the precast concrete components 2.0 project that I've spoken about, the effects on the initial design may be rather minor. But if we also consider extremely heterogeneous components like rubble or demolition debris as ready-to-use building materials and use them as is, the outcome may very well question our current notion of aesthetics. The takeaway here is that designing with what is available constitutes itself as a fundamentally different practice than being able to manufacture every form at will, like in mass customization. And in contrast to the aesthetic style of discreteness and computational brutalism that are already fairly established and can be seen as a contemporary architectural paradigm, a design language using pieces of rubble and debris is still to be found. So we have seen something like this before today, so I hope this ties in quite well. This is how Midjourney, an AI system capable of creating images from a natural language caption, imagines buildings built from reused components to look like. And we have made quite a few of these queries in different detail, but the results are always very similar. There simply is no real design language yet that corresponds with the reuse of building components. The resulting images are a mashup of architectural elements like windows, columns, and slabs put together in a seemingly deconstructivistic architectural collage. Here is another example with a much simpler query, leaving out a lot of the detailed specifications, but the outcome is overall rather similar. We get a potpourri of elements that are puzzled together, but we can't identify what the individual parts really are. So reusing building components seems to be commonly associated with this kind of mashup aesthetic. And it is no wonder that an image-based AI system cannot deal with the aesthetics of reusing building components, since there are only a handful of projects that really work with this idea of reusing whole building components, let alone pieces of rubble and debris. So the concept of reuse is not tied to a specific style yet. It can lead to a new computational brutalist style, like in the reference to the left, which is a work by students of the Bartlett School of Architecture, but it may as well be hidden, like in the project on the right, by Architecture Studio In Situ, which is an extension of a building completely built from reused building components and materials. In a recently held studio at DDU, students were asked to speculate on the transformation of a parking garage into a center for circular economy. And the task was to come up with a design that reuses building components and debris stemming from that same parking garage. And this student based her design on a central sculpture fulfilling multiple purposes throughout the different stories of the building. And the sculpture is aggregated from leftover parts from a flood catastrophe, as well as components that are disassembled from the parking garage itself during its redesign. So the idea here was to reuse what can be used from flooding debris instead of mindlessly discarding it as waste. And with this concept in mind, the student informed her design of the reimagined parking garage. And our takeaway here is that if we want to rethink architectural design, engineering, and construction in a circular manner, the whole process chain needs to be considered. This means that we should not only speculate and design by focusing on the site and the program, but also in parallel speculate on the processes involved in construction, think within these processes, redesign these processes, and create new ones. So we encourage our students to do exactly that, think, speculate, and design while considering not only site and program, but also real digital circular process chains. This is another student work that was done within the same design studio. And for testing and experimentation, the students again were given a simplified version of our computational modeling pipeline that enabled them to perform demand-based matching of components, as I've shown before. This student came up with the idea of arranging the harvested components into modular boxes, serving as rooms for the transformed building, similar to a freight container. These containers could then be stacked and moved by an automated crane, ever changing the configuration and thus also the program of the building as needed. And at the same time, serving as a material repository for the reused components, keeping them in the loop for future reuse scenarios. And this concept of keeping whole building components in the loop as long as possible is exactly what we set out for in our research project, The concept of perceiving buildings not only in their current state, with their current program at a specific point in time, but also as component repository for future buildings, letting the building components circulate through time and space. So I hope I could give you some insights and open for questions. Thank you very much.
Thank you. That was very, very interesting. We have now time for questions or comments. You were... yeah.
Thank you. Very good presentation. Just a short question out of curiosity. Are you aware of these kind of more historical examples of this kind of work? For example, the Roman technique of spolia, using kind of previously erected buildings for constructing something new, even something very kind of big, like a triumph arch or something like that.
Yes, this is actually like what gave the inspiration to start this whole process at our unit. We made a publication called Rethinking Spolia in the current times, basically. And this like research on spolia was really what kicked things off in this kind of research trajectory. But we are also aware that spolia is something where the component was really like used as a trophy, as a prize from war, basically. And of course, this is not what we're trying to do. So we really just want to start off the process and think about how can we reuse materials that are in buildings and still perfectly fine, considering structural capacity and stuff. And how can we reuse this instead of like demolishing everything and like producing new stuff all over again? So yeah, it's basically like recontextualized spolia maybe.
Thank you. Very interesting presentation. And I actually, for me, the most interesting moment was when you were comparing the partlet rendering with the picture next to it, that actually used or reused, or that was solely built out of reused material. And I was just wondering, like, as you said, the process is what's changing the architecture. Changing the process of it is actually what that leads to the changes in architecture. And I'm wondering how much the end result, the end object, should be capable of speaking or discussing or saying what the process have been. So how much the aesthetics of the space should be telling how it was built and out of what. Because like comparing those two images, I think one has really strong aesthetical ambitions, and the other one at the same time, you might not even understand how it's constructed. So I'm wondering if the object can speak for itself. Should it be able to, and what kind of aesthetics are the ones that actually would educate us to make this change, to start reusing the construction materials?
Yeah, this is a very good question, and I'm afraid like I can't give you like a definitive answer. And I'm thinking about the same things, and there are different positions to that argument, I guess. So there are studios, and also a friend of mine is always arguing like it shouldn't be hidden away, like the architectural design should not be influenced by the process of how the architecture is being built. And to be honest, I would argue exactly opposite. I would argue the architectural design, the objects should reflect how this building or how the structure was conceived. So I also picked these two examples because they are so different, and I'm more, at least currently, I would say more like I really love this style of the Bartlett School of Architecture because it's really radical and it shows that there is something new. We are doing something new. We are taking natural materials and just perform minimal changes to them, and then we use them as architectural building components. And I think this is where a new kind of aesthetic paradigm may be developed. We don't know yet, I would say. But I think both techniques, so to speak, have their own relevance. Like, I mean, looking at the in situ project, when I found out that it is completely constructed from reused materials, it was also kind of mind-blowing to me because it looks so conventional, and I don't mean that in a bad sense. It's just they had an architectural design and they like hand-picked the materials and components to use for that design. And this is also, this is also architectural practice to pick the stuff that is right for your design, I would argue.
Thank you very much to introduce us to how the circular works and how digital techniques can help how to do that. And you told more, of course. What I was thinking, I remembered the practice of Lucien Krol, the Belgian architect, and he was one of the first pioneers who started to work with the computer, and he was very interested in participating with students, the inhabitants, and to come to a kind of architecture which is not designed by the architect but by the collective, and using the computer to allow the individuals who, like students, design their own facade. So if a student wants a small window, gets a small window, a big one. And so he made a palette of a lot of variations. And then what you get was a kind of image which you now see by reusing material and finding the right way to combine them. So it produces another image. In Lucien Krol's case, the most famous one is in Leuven. It looks, roughly speaking, the same as what we see here. But what I was wondering, his image or his architecture, so also the floor plans, etc., because also in your case it's spatial, was to empower the individual and the collective. So in a way to get rid of the author, to get rid of the architect, but you provide a technology which helps a kind of spontaneity of the group of the people making a building. That was in the 60s and 70s. So I was wondering now, if we have this advanced digital working and reworking of material, who controls the buttons? So shouldn't you just give this technology to, when you do housing, to the people so they can design their house self? So then the expression of the form is connected to a choice of content and is not, which is fascinating, I think, produced how things fit together or not. So my question would be, where does inhabitation or the architectural spatial program come in? So so how is the content, or could the content be connected to the form? Instead of that, it's just a fascinating accident, but I think it could be mobilized for something to break official codes like Lucien Krol did, who was an anarchist who wanted to give the power to the people.
Yeah, I mean, that's an excellent question. And I'm afraid it's also one that I can't shoot an answer right now, of course. I definitely see, to refer to your talk, the gentleness in that approach, by caring about the people who are later inhabiting the building. One example now comes to mind, which is the Circular House in Berlin, which is actually a project from a German startup that also deals with reusing building components, but not structural components, so more like windows and components of a bathroom and stuff like that. And they actually were planning new headquarters, and they always invited everyone to just come in and plan with them their new headquarters completely from reused materials. So I think this is a very interesting practice, and like if I would decide it, I would just say, hey, here is this technology, this digital technology, like please everyone use it. I'm really like an open source enthusiast, so once it's at a certain point where it's actually usable, I would definitely argue it to give it away to everyone that wants to use it. And in that sense, I would definitely, go with that argument and saying everyone that later lived there should be involved in the planning. And if they want to have like large windows, they should have large windows, of course. And I think this is also the idea of the approach, not saying, hey, yeah, you can't have that because it's just not possible. It's more like, okay, I want to have this. This is my architectural vision. This is my design. Please tell me what could fit. And if nothing fits, you still have the option to say, okay, I'm just going to produce this one part as a new component, and then it can be reused by another one in 50 years or in 20 years. So, yeah. Thanks for this inspiring question.